So and this representation is called a faithful. This representation is called a faithful if phi is 1 1. It's called a faithful. It is called faithful representation. It's called faithful if phi is 1 1. So if the representation phi from a semigroup S to Tx is also 1 1, it's first a morphism. If it's also 1 1, then such a representation is called faithful. So now we prove a theorem which is the analog of Cayley's theorem. Which is the analog of Cayley's theorem. Here we show that if S is a semigroup, that's the theorem. If S is a semigroup, and let's define X which is equal to S1, the semigroup S adjoined with an identity S1. Then there is a faithful representation. Then there is a faithful representation phi from S to Tx where X is S1. Okay, so let's define this representation here. So every semigroup S can be represented by maps actually. Yeah? For any semigroup S, we can choose X equal to S1. Then we define a map from S to Tx, which is a morphism and 1 1. Proof. Let's define this map. Define phi from S to Tx by. Let's define this map by X phi is equal to. So let's define for all A in S. Define for all A in S a map phi A. Like in case of Cayley theorem, we define map phi A from S to Tx by just the product here, like in Cayley's theorem, Xa. It's a map from S to Tx. It's a map from, it's a map. First we define for all A in S, we define a map phi A from S to S. Okay, let's define this map. For all A in S, define a map phi A from S1 to S1. Okay, from S1 to S1 by phi X is equal to Xa. Okay, so phi is a map from S1 to S1. So then this phi it belongs to Tx. Okay, it's a map from S1 to, because S1 is equal to Tx. So define for all A in S, define a map phi A from S1 to S1. For all A in S, like in groups, for all A in G, define a map from FA from G to G by equal to AG. So same is here. For each A in S, we define a map phi A from S1 to S1 by X phi A is equal to Xa. So this phi A is in Tx. Now we define a map now. Define psi from S to Tx by A psi is equal to phi A. So now it's clear, because phi A is in Tx. Phi A is in Tx. Okay, we'll see that this map is a morphism. Then for all A comma B belongs to S, AB psi is equal to phi AB, and you can see this same as phi A phi B, and that's equal to A psi and B psi. You can easily verify this. You just need to verify this. Phi AB is same as phi A phi B. they are equal maps. It's the composition of two mappings phi A and phi B, because phi A is an element of Tx, phi B is an element of Tx. So you can easily verify this. They are equal, and if you want to verify it, so let's check it. X of phi AB, it's equal to x into AB by definition, x AB. And if I check this x, so let's verify it here. If I verify this, x phi A phi B, let's apply first phi A, it's equal to xa, then apply phi B on this element xa, which is equal to xab. So x phi A phi B, it's equal to, first apply phi A on x, which is equal to xa, then apply phi B on xa, which is equal to xab. So both are equal. X phi AB is equal to xab, x phi A phi B, it's same as xab. So that means they are equal at each point of S1. So therefore they are equal maps. Phi AB is same as phi A phi B. And now we verify that it's also 1. It's a morphism. Now we show that it's 1. So we need to show that this representation should be faithful. So therefore phi is a representation. Therefore psi, so therefore psi is a representation of S by maps in Tx, in Ts1 actually, because X is at S1. Now we show that this psi is faithful. Now we show that psi is faithful. Psi is faithful. Psi is faithful means it's 1. Means 1. So let's choose. I need to find what psi is a map from. Psi is a map from S to Tx. Let us choose any 2 points in S. So let S1 comma S2 belongs to S, such that S1 psi is same as S2 psi. They are equal. And this means, by our definition, what's S1A, it's what's A psi, it's equal to phi A, so it's equal to phi S1. Phi S1 is equal to phi S2. So they are equal maps in Tx. So which implies x phi S1 is equal to x phi S2 for all x in S1, because phi S1 and phi S2, it's a map from X to X. It's a map from X to X. So they are equal at each point of X, because S1 is equal to X. So which implies that by definition it's equal to X S1 is equal to X S2 for all X belongs to S1. So in particular it's true for X equal to 1, because 1 belongs to S1. So which implies 1 S1 is equal to 1 S2. This implies S1 is equal to S2. So thus the representation is faithful. So therefore every semigroup S is isomorphic to some. Therefore every semigroup S is isomorphic to some transformation semigroup. So therefore every semigroup S is isomorphic to some subsemigroup of Tx. So it is isomorphic to actually some transformation semigroup, because all the subsemigroups of Tx are called transformation semigroup. So that proves the analog of Cayley's theorem in case of semigroups. Now next we define a very important class of semigroup, that's called a rectangular bands. So definition of rectangular band first. Definition. So then we explain why we call it a rectangular band. A semigroup S is called a rectangular band. If for all A, B in S, A, B, A is equal to A. If it satisfies this identity, okay, then it's called a rectangular band. Rectangular bands. Now next we have very important theorem on rectangular bands. Let S be a semigroup, then following conditions are equivalent. Let S be a semigroup, then following conditions are equivalent. The first condition is S is a rectangular band. S is a rectangular band, and second condition is every element of S is idempotent. Every element of S is an idempotent. Idempotent means the square of every element is equal to the element itself. So for all element A in S, A square is equal to A. Every element of S is an idempotent, and it satisfies one more condition. A, B, C is equal to AC for all A, B, C in S. So S is rectangular band. Then second condition, every element of S is an idempotent, and ABC is equal to AC for all ABC in S. And third third property, there is a left zero semigroup. There is a left zero. There is a left zero semigroup which we will denote by L, and a right zero semigroup R. There are two semigroups L and R. One is called left zero and second one is right zero, such that this S is isomorphic to L cross R. And the fourth property is S is isomorphic to A cross B. S is isomorphic to a semigroup, isomorphic to a semigroup A, to a semigroup A cross B, to a semigroup A cross B, where A and B are non-empty sets. They are not semigroups. A and B are not semigroups. They are non-empty sets. A and B are. So this condition is very important. Are non-empty sets, such that, but this A cross B, it's a semigroup such that the product is given by, such that the multiplication on A cross B is given by this multiplication is given by, let's take any two elements A1 B1 into A2 B2. This multiplication of two elements in A cross B, it's equal to A1 B2. The first element of this ordered pair and the second element of this ordered pair. It's A1 B2. So this is very important. This theorem is very important, and because of this fourth property, because it's equivalent to the semigroup S, for a semigroup S to be a rectangular band, S is a rectangular band if and only if it satisfies this property, and because of this property of the rectangular band, it's called because of this property of a semigroup S to be a rectangular band, gives the meaning that why we call a semigroup S a rectangular band, because of this condition actually. A1 B1 cross A2 B2 is equal to A1 B2. And if I write A2 B2 cross A1 and B1, it will be equal to A2 B1. So it's actually like this. If you want to see this, suppose we have a 2 points are given for this rectangle, say A1 B1, and this is here say A2 B2. A2 B2. Now what's the product? A1 B1 cross A2 B2 is A1 B2, and A1 B2 is this one actually. So if I know only two vertices of the rectangle, then I can find the other two vertices of the rectangle by means of a product actually, because this one is A1 B2, it's A1 and B2. And what's this? This one, it's the product of these two, because A2 B2 into A1 B1, it's equal to A2 B1. That's A2 B1. That's the vertex of this. That's this vertex of that this rectangle. So if I have only two vertices are given for this rectangle, then this vertex is the product of these two, product of A1 B1 and A2 B2, and this one, it's the product of A2 B2 and A1 B1. So that's why it's called a rectangular band. So let's prove these four conditions. They are actually equivalent. So first we suppose that S is, first we prove 1 implies 2. We assume that S is a rectangular band, and we need to show that every element of S is an idempotent and it satisfies this property. So proof. First implies second. So assume S is a rectangular band. Assume S is rectangular band. Then by given condition ABA is equal to A for all AB belongs to S. So we show that every element is rectangular, every element is idempotent. So we have, if I set B equal to A, we have A into A into A is equal to A, which implies A cube is equal to A. So this implies A power 4 is equal to A square. So let's name it 1 here. Now if I replace B by A square, because it is true for all A, B and S, by putting B equal to A square in this identity, ABA is equal to A, we see that A square A is equal to A. So which implies, because ABA is equal to A, so that means A instead of B, if I will write B square, it's called, if I write A square here instead of B, so it means A square A is equal to A. So that means A power 4 is equal to A, name it second. From first and second, because here A power 4 is equal to A square, and here A power 4 is equal to A. So from first and second, A is equal to A square. So therefore every element of a semigroup S is an idempotent. Now we prove the next property. We need to show that the first property, this S is rectangular band, defined on S, every element of S is an idempotent, that we have seen. Now we show that for all ABC in S, ABC is equal to AC. So now let ABC belongs to S. So then by our given property, then ABA is equal to A, because of this it's given, and I can write CBC is equal to C. This is also true. And one more thing, B is equal to BACB. So ABA is equal to A, CBC is equal to C, BACB. So this is an element of S. BACB is equal to B. Now AC is equal to. Now I will calculate AC. What's AC? AC is equal to this thing, BACB here. Or you can say what's AC actually here? It's actually ABA is ABA and C is CBC. It's equal to ABA into CBC. And that's equal to A, using associative lights, BACB. BACB, and then here C. And that's what's BACB. BACB, it's equal to B. So it's equal to ABC. So AC is equal to ABC. So that's what we have to prove. Actually, every element of S in I put it, and for all A, B, C in S, A, B, C is equal to AC. So A, B, C is equal to AC. Okay, A, B, C. So AC, A is equal to A, B, A, C is equal to C, B, C, A, B, A, C, B, C. Then I apply the associative law of semigroups here. It will be equal to A times B, A, C, B, B, A, C, B, then C. But B, A, C, B is equal to B. B, A, C, B is equal to B. So it's equal to A, B, C. So that proves 1 implies 2. Now we prove second implies third. Second implies third. So assume every element of S is an idempotent, and A, B, C is equal to AC for all A, B, C belongs to S. Suppose this is true, and we show that S is isomorphic to left 0 semigroup and right 0 semigroup. So let's fix some element C of S. So let C belongs to S. Choose any element C and fix it, and let's write here L is equal to S into C. It's a product of elements of S with C, set of all such elements. And let's write R is equal to CS. Okay. Then we see that L is a left 0 semigroup and R is a right 0 semigroup. And we will also show that S is isomorphic to L cross R. Okay. First we verify that this L is left 0. We show that L is left 0 and R is right 0 semigroup. So for this I have to choose two elements from L. So let's choose two elements. Let X, Y belongs to L. What is L? L is equal to SC. So this implies X is equal to element of S times C. It's equal to AC, and Y is equal to BC, where A, B they belongs to S, because X is in SC. So X is the element of S times C. It's A into C, where A belongs to S, and Y is it's also in SC. So it's equal to B into C, where B is in S. Then I will find the product XY. What's XY? It's equal to AC into BC. So I need to show that it's a left 0. That means this every element of L should be left 0. Which, in other words, I mean to show that XY should be equal to X. X should be the left 0. So here it's equal to A